I think everyone that wants to join has joined. All right, so let's get started then. First of all, welcome to this session. It's a great pleasure to be here. And so today I'm going to talk about a system that can be made that automatically and in real time detects early signs of sepsis in neonatal patients. So that is the one-liner that we're going to talk about today. Now, first of all, a little bit more context. First things first, my name is Victor. I'm from ML6. I'm a machine learning engineer there. And we've actually partnered with some great doctors that are being seen here on screen. So David van Laren and Maurice Meus are the biggest contributors here. So they're awesome. And together with them, ML6 has developed a machine learning system to support hemodynamic intervention in the neonatal intensive care unit. So this is a paper that was published as well. As you can see, I was the co-author, so this is why I'm giving the talk. And the bit.ly link is put here. So if you're fast, you can type it over. If you want, I can also put it in the chat at the end of the talk. So this is why I'm talking about this. And I hope to give you some insights into the different learnings that we've had, into the different things you have to take into account when you want to do this kind of machine learning in a medical field. So it's just a pretty technical view on what to do. So let's start with the current process in the NICU. So the NICU is the neonatal intensive care unit. Of course, everything is centered around the patient. So a patient is a preborn or like a prematurely born baby. And so the NICU is the intensive care unit of the neonates. So this means that the only children that are there are actually already in quite a bad condition. So it's paramount to try and get to infections or like flag infections way before they ever get there, because it can be too late very, very soon. So everything starts with the patient, but of course, it's a hospital, so there's a lot of patients. You have several babies, and you only have that much personnel, right? So in the NICU, of course, it's a neonatal intensive care unit. Of course, there's going to be more staff than you usually have in different parts of the hospital, but still, you only have limited staff for several babies. So it's not like you can monitor these patients 24/7 with a doctor each. Like that's simply impossible. So the big part of this, so the big thing to remember here is that you only have one doctor for, let's say, 7 patients or 6 patients in this case, and they go by a schedule, right? So they go and check in on the patient. They basically take a look clinically, and then they make up their mind. So they say, okay, everything is going well, or everything is not going well, and they do this for every patient. But of course, while a doctor is looking at one patient, they can't really be looking at other patients at the same time. So to help with this, every single patient is hooked up to a kind of monitor that is continuously capturing the life signs, let's say, so like heartbeat, for example. And this gets then piped into what are called the monitor walls. And these are simply readouts from every patient's condition at every single time. And a lot of people, like the nurses and stuff, they are looking into this. So they can continuously monitor these screens. So that makes it a little better. So now you have both the screen monitoring and then the doctor that is doing his routine or her routine checkups. And then when one of these monitors goes awry, when, for example, the heartbeat goes out of whack, then that monitor can send a request or like an alarm to the monitor wall, and one of the people looking at the monitor wall can then alert or either go check themselves or alert the doctor, and then they can heighten their they can heighten their care for that specific patient. So that's what we're talking about here. Now, there are some caveats to this alarm system. So while it's very, very good, and while it certainly allows for better monitoring of the patient than only the doctor ever could, there are some drawbacks to the system. And so I've listed them here. Actually, they're like thresholds So this means that when a heartbeat goes above or below a certain threshold, and usually this is a statistically derived z-score, the alarm goes off, right? This does not always mean that it's supposed to go off. So there you have quite a lot of false positives because, yeah, a heartbeat can go for whatever reason up or down. You have, yeah, I mean, it's a lot more complex than just a threshold, right? So there is the limitation there. And then also it's independent of patient context. So like I said, it's derived z-score, so it's statistically, and by definition, in the intensive care unit, you're not going to have your run-of-the-mill patient, right? So by default, you're already going to have patients that might not fit that z-score, might not fit the average per patient, let's say. So that's something to take into account as well. Also, and this is also quite a big one, alarms are single signal. So this means that if you have multiple signals coming from a patient, let's say heartbeat or respiratory rate, things like that, every alarm only looks at a single signal. So an alarm will flag if, for example, the heartbeat goes out of whack, but if everything else is still fine, it doesn't look at that. So that does inhibit a lot of these false positives, because you can have, for example, a sensor that's falling off, for example, and then that alarm will go crazy, but there's nothing happening. There's also no adequate multivariable visualization. So like I said, all of those data from all of those monitors are being captured on screen. The nurses can look at those screens, but there isn't that good of a visualization out there yet that can basically visualize different trends over different variables at the same time. So you can only basically do the same thing as the monitor can and look signal by signal. And this all means that it's largely reactive care. So this means that for the most part, if a patient has an alarm or goes into shock or whatever, the alarms are usually there only to get the person that needs to be there as fast as possible, right? But it's not proactive. It can't predict it. It's basically just saying, right now is actually already a little bit too late. Let's try to limit the damage. That's what it's trying to do, because it's not smarter than that. And that's what we're trying to do it better, let's say. So then the question starts brewing in your mind if you see this, like, what if we can utilize machine learning to predict, for example, sepsis? Sepsis is blood poisoning. It's relatively, it's very dangerous, especially at that age, and every minute counts. So if you can get there when only the symptoms are coming up yet, but there is no shock, for example, yet, then that's a great deal of value. So that would be perfect. And then you could basically alert the doctors or the nurses to go check up on that patient a lot sooner than the alarms might have gone off, because you spotted trends that are like similar when you go into shock or get sepsis. And that way we can try to get proactive care in place instead of reactive care. So that was kind of the idea. Like, let's try and do that. And so let the machine learning begin. This is where we can use machine learning to try and predict an outcome, right? And so there are several different fields in machine learning that we could have used. For example, the first one is supervised learning. You can see it on the left here. You start with data with labels. This means you have to have a relatively high or relatively large data set, and then you have to be able to say, that was sepsis, that was not sepsis, that was sepsis, that was not sepsis. Just a simple yes or no, in such a way that the machine learning model can train on that. It can generate its own rules to try and find that sepsis. And so that's what the supervised learning algorithm is going to do. So basically, it's going to output a class, and if that class is wrong, a class could be either having sepsis or not having sepsis, two classes. If that class is wrong, you get an error, and that error signal basically trains the model to do better next time. And so that's why you need the labels, because you can't really get the error without the labels. You can't find what it did wrong if you don't know what the right answer was. And so that's supervised learning. It's relatively the most powerful version out of the three, let's say, and definitely the most used. So then in the middle, we have unsupervised learning, which basically does about the same thing. So you could have data without labels and then try to say, okay, cluster me these patients, let's say, or these time windows. And then you could have like big clusters of patients that look alike and are similar. And then maybe you have outliers or anomalies or smaller clusters that tend to have a lot of patients in it that don't do so well. And that might help you. But again, because you don't have labels, it's very hard to say if it's correct or if it's the right way to go. So if you have labels or can obtain labels, it's usually a better idea to go into supervised learning. And then you also have reinforcement learning, which is a bit of an odd ones out, but this is actually for the next stage. And it's more like interacting. So you have a certain environment, let's say the NICU, and you can have a reinforcement learning agent do actions on it. Let's say send a doctor or apply a certain medication or things like that. And then based on that action, the environment will change. So because a doctor has now been called, the environment, being the NICU, has changed because a doctor has now taken a look at the baby, at the patient. And then based on whether or not that was a good thing that the computer did, it might receive a reward or a penalty. And that is like here, the error term is, it trains the reinforcement learning agent to do better. This is relatively experimental, but it could give an idea into the future on where these kind of algorithms can actually make decisions, but we're not there yet. So let's focus on supervised learning for now, because we actually did have labels, and this is what we focused on, let's say, and I would advise the same thing. So we also did unsupervised learning, and it was pretty difficult to get like a clear way out, because also sensor faults or things like that also fall under the category anomaly. So in machine learning, we usually use the term pipeline, because you usually have a certain amount of steps that are sequential, that come behind after each other. And this is ours, right? So this is the pipeline that you might want to use when you want to develop a real-time machine learning application in medical care. So the first thing is data processing. We're going to go over each of these parts: data processing, feature engineering, machine learning itself, and then sliding window evaluation. And each of these has some learnings or some challenges that might be very relevant if you're trying to do the same thing or a very similar thing. So as a machine learning engineer, it was actually quite, I was actually immediately trying to tie different parts of the industry together and try to find, okay, how have we done this before? Like, how could we compare this to this task of trying to figure out whether or not a patient has sepsis or not? And the first thing that popped to mind is predictive analytics or predictive maintenance. And what that basically means is you take a machine, like let's take a wind turbine or an assembly machine, and you have data of sensors that are on those machines, and you have data of those machines breaking. And then every time a machine is broken, you have a label. And then based on the sensor data in front of that label, right before that label, you might actually be able to train a machine learning model to detect those even before it actually fell down, even before it actually broke. So that's the main idea. Now, for several reasons, that is not a good way to go about it. So like I said, I did it because I did this before, but for several reasons, you can't use the same logic in medical care. So for example, for one, a patient doesn't break. It might seem stupid, but it means that a doctor will never let it get as far as maybe a wind turbine breaking or a machine stopping. Like, they will always try to intervene before, even if they're not certain. They will give it the benefit of the doubt and deliver antibiotics, for example, anyway. So it's not as simple as saying this one had sepsis and this one didn't, because usually you don't really know yet, or even after the fact, it's difficult sometimes to say, because you need a test, which is not always 100%. So you have a test that determines 24 hours later whether or not the patient had sepsis before, but in that time frame, a doctor might well have already administered antibiotics, or in that time, the test might have not been correct. And so there are several different branches of labels that are not as clear-cut as having sepsis or not having sepsis. They will also be given antibiotics, like I said, in those 24 hours, which spoil a little bit the signs, because it might well be that they didn't have sepsis and now they have antibiotics and they react to it in a certain way. And now those signs go up and down and we don't really know why. In another way, or you can also recover autonomously. So even without antibiotics, it's possible that a baby or a patient can just, its immune system is strong enough and that it takes care of the sepsis even without intervention. And so by then you might have seen the signs of sepsis in the data, but it wasn't labeled because it was never seen as sepsis and it just got there automatically or autonomously. And so these labels range from shock, which is very clearly sepsis, to suspected sepsis and everything in between. And it's not always as clear cut as might be in, for example, a case where a machine breaks. So this is already something to take care of, and you will have to, in the paper, it's written more in depth. You will have to take care to define well how you define those labels, because it's not always that easy. Then the second part of pre-processing is the sliding window. So what you eventually want as a system is a system that can look at a certain amount of data. So let's say on the left we have the birth, on the right we have discharge. You have the timeline in between of this patient's stay at the hospital. And what you want to do is basically we look at a certain amount of data, and then for the next minute, let's say, we try to predict a probability of that patient having sepsis based on the data of the previous 24 hours or 12 hours. Doesn't really matter this case. And we basically want that window, that 12 or 24 hours, the red bar, we want that to slide, because for the next half an hour, we want to basically look at the last 24 hours again, but then it gets less far into the history. So in that way, you actually keep a 12 or 24 hour block, and you basically slide that over the time that the patient is there and always detect at the present, based on the last values, sensor values. So we keep going, and then in the end, we have a sort of graph over time that explains us, or that tells us, okay, what is the probability of sepsis over time? And again, you have to see this in a real-time perspective, so you don't already know when it's going to drop when you're, for example, here. Or you don't know if this drop is going to be, or this peak is going to be as high as the previous one. So it's very difficult to not look at the future data because we don't have that yet in the current application. And so this is what is called a sliding window. And it's a very important term because I'm going to keep using it, since this is going to be our unit of machine learning. So this is what we're going to do the machine learning on, not on the patients. And this is exactly what I was talking about. So you have data selection. And at first you might think, okay, we have, let's say, 700 patients in our data set, right? And several of them, let's say 50, have gotten sepsis at some point. Right? So it's very easy to think, okay, we have actually quite a lot of data, and we have about 50 out of 700 positive cases. So it's quite nice. But you have to remember that the patients here aren't the unit of machine learning. It's the time windows that are the unit of machine learning. And so you have several patients, but some of those patients have hundreds of maybe thousands or maybe tens of thousands windows that are just not sepsis. And then maybe one out of the maybe 10,000 windows of a patient that actually got sepsis contains signs of sepsis, right? And so that's something you have to take care of. Is not, you have an incredible class imbalance because you have only a few examples of where it was sepsis and only an immense amount of data where it wasn't sepsis. And so those two are very imbalanced, and it's something to take care of. Usually in literature, you do under or over selection. We actually did under selection, so we made basically the amount of normal windows about equal to the amount of sick windows, but it's still a huge class imbalance. So take care of that. And then even then, still, you have questionable windows, let's say. So you have windows in which the person was, or the patient was under antibiotic, right? So do we include that or not? Because at that point, you might have sepsis, but not see the signs of it because of the antibiotics. Or the other way around, you might have weird reactions on the antibiotics without actually having there been any sepsis. Also, very important, you can only use the signals that are present in almost every single window. If you have signals that are only available in certain windows, it's very difficult to do in a real-time manner because you can't just create data out of thin air. And also it's very difficult to train because then you have selection bias in which you only take the data or the signals that are, or only take the time windows, that had those signals inside. So a lot of these signals are, for example, lab tests that are custom demanded. So that means that if a doctor actually demanded a lab test, it means that there is already suspicion that something is going on. And you can't just take only those windows because then you take prior knowledge into account. Something, again, we might not have in the real-time context because by definition, we want to find those that haven't been found yet. And also you have patients with complications. There is the NICU, so the neonatal intensive care unit. Some of them are in a pretty bad state and might not be representative for a normal child. And so basically a normal or a normal trained machine learning model might just almost constantly say that something is wrong because this patient's signals are just all over the place. And so these are kind of the decisions that you will have to make yourself based on the domain knowledge. So now we have the time windows. We have selected which time windows we want. So there is now feature engineering. So if you have a time window, you have within that time window several signals, right? Let's say our time window is 12 hours long, for example. You have heartbeat of 12 hours, you have respiratory rate of 12 hours, and so on and so on. Now, these are way too many data points to give to a machine learning model. So what we want to do is we want to try and get as much value out of those signals without actually destroying them, right? So get as small as possible in the data space. And so what we're going to do is for every single signal, we're going to create a certain amount of features. And features could be as simple as minimum, maximum, or average. But they can be very, very complex based on domain knowledge, on what the doctors are looking at in the data, try to interpret that and put that into mathematical terms to actually generate automatically. And based on these features then, those features we can then give to the machine learning model. And you can see it as, at that point, the machine learning model got a kind of summary of the data, a summary that should have enough data or should have enough value, let's say, left to actually make the decision. So that's why we do feature extraction, mainly because it's just too much data to work with otherwise. And those machine learning models can't sift through everything. Except when you use deep learning. But there is a caveat there. So like I said, we generated our features manually. There are ways to circumvent this. So you have deep learning versus classical machine learning. And time series classification is what we're doing, right? So you could see it as a time series. You have a data point for every timestamp. The reason why we chose to make handcrafted features. So on the right, the difference between the two, deep learning or feature engineering, is that in feature engineering, you make the features yourself. Like I said before, in this way, you define whether or not to get minimum, maximum, and everything else out. On the other side, you have deep learning, which will try to generate those features or try to learn those features from the data, right? So this is the main difference between the two ways. In this, deep learning is going to try and define its own features, regardless of domain knowledge, just out of the data. This means that it's highly complex, whereas handcrafted is mediumly complex because you have more in hand. There is more that you can know of than in the deep learning side. And inevitably, and this was a very big part of the project, it should be interpretable. Because if a doctor is going to make a decision based on the outcome of that machine learning model, he better know why the machine learning model did what it did. And that's something that is very easy to do in handcrafted features because the features mean something. They are proxies for what a doctor would look at. Whereas in deep learning, the interpretability is low because the features are generated by the model itself and might not actually mean something in human terms. So it's sometimes very difficult to figure out where a deep learning model is looking at versus a classical machine learning model that just basically tries to weigh different factors that you can actually define yourself. And so a side effect of having to generate those features based on the data is that deep learning usually needs a lot of data because you need to learn that much more, whereas in handcrafted features, a lot of the domain knowledge, the knowledge that we already have, is put into those features already. So it only needs to combine those features based on the data, which is a lot less connections to make. So this is the trade-off that you might want to search for. Now, when you can do deep learning, it's actually really interesting to do so because it can sometimes get features that might not otherwise have been spotted. So that is the big power of deep learning, but it has some drawbacks as well. So like I said before, let's recap. You have all of these time windows. That's a lot. And now we want to be able to find those time windows that contain signs of sepsis, right? That is the ultimate goal. So if we want to project this into how would this work in the clinical setting, it's basically a machine that looks at the last 12 hours of data and then makes its prediction maybe every minute or every 15 minutes, something like that. And so that's where the evaluation comes in. And so I skipped a few. So what you might do at first when training the model is you take all of these windows that do not contain any signs of sepsis, and you take all of these windows that contain signs of sepsis. And then you basically squish them together. And again, like I said, you have to under sample because the amount of white windows here, so without sepsis, are way too high to compare directly to the amount that do have sepsis inside. So you want to try to keep that like about at the 10:1 ratio maximum. And so if you then go to the next part, then basically, I'm going to go to the question later. So basically, what you do here is you take those windows and you split them up into its features. So you generate those features for every sliding window that you have or that you want to compare. So that includes all of the sepsis windows and all of the normal windows. And then you basically split those up into a training set that has a certain amount of white and red windows or features, and then a test set. And then you're going to train your model on the training set, and then you're going to apply it on the test set. And then because you know what the test set should be like, you can actually try and figure out how well the model does. This would be the classical way of doing things, which we severely say, don't do this. You should do this, but don't evaluate your model based on this. And the reason is that this is not the way the model will be run in the real world. And this is a very big one. Never evaluate your model in a different way as the way it will be used in a real-time setting. Because we actually got very good results on this method by just using a training set, having a test set, combining it, and then we could publish a paper simply on this because we beat the state of the art. But this is not the way it's going to be run, because we trained with about equal as much white windows as red windows, but that's not how the real world works. We have so many more white windows than we have red windows. And how would you, if you have this graph again, when would you say the model was correct? It's very difficult to assess the performance. So evaluate the models, how they will be used. And so one of the reasons this is so important is, for example, if you have this graph, when it peaks out after the fact, is it still correct? It still detected it, but it wasn't faster. So was it a correct prediction? You also have multiple predictions that form a peak. So this peak might as well be over the threshold that you might set for 3 times or for 3 consecutive times, but that's actually one time that people will actually take that for its face value. So they will only send a doctor once for those 3 high predictions. So 1 high prediction or 10 high predictions does not mean 10 instances of sepsis detected. It means one continuous instance. So that's something you have to take care of. And then also false positive. How are you going to say a false positive? We had, for example, one false positive that was a false positive, but it basically peaked because the child had just received a vaccine, which is also a very similar reaction to sepsis. So was that wrong? Was that not wrong? It's something you have to decide. This is actually why it's so interesting, because it's not really been done before. These are all open questions. So we have done it our way. That probably papers will appear later on that as well. So I can't talk too much about it yet. But yeah, it's basically open for the taking still. And that's what I advise you doing, is experiment with this. Try and figure this out. This is a body of knowledge that has not yet been tapped, but that should be. So to recap, we're not there yet, right? But we're on our way. So we're laying the foundations, we're trying things. It was actually very cool to see how this worked. I have a slide on this later. So don't take this for granted. We're not there yet, but it's very, very interesting. And the amount of data, especially, but also the machine learning models are getting there in terms of interpretability, in terms of being able to be applied in a real-time setting to actually make a difference in this field. So as a conclusion, the model that I showed you today, we made many decisions and assumptions, as I just said, but the model that we came up with showed very promising results in the first tests. So it's currently undergoing more testing, like a longer stage of testing and real-world application, getting ready for clinical trial. So the whole idea is that we now want to do the finishing touches, or mainly the authors of the paper now want to do the finishing touches, and actually get it tested so that we can actually in real life see how well it performs. Because like I said, it's very difficult to gauge from that graph how well it's doing. And then techniques are applicable for many more cases. So that's basically, if you're not a neonatal doctor, it doesn't really matter, because this is basically trying to find a condition based on real-time signals, like vital signals from patients. And which patients doesn't really matter that much. So it's a very broad application area that you might use this in. And if you work in this area, I very, very highly recommend we try and work this out, because it can mean a big deal. It can monitor patients 24/7 and help save precious minutes or even hours. So we saw that not all the time, but often we saw that the monitor actually came up ahead of a possible diagnosis by a doctor, sometimes by even an hour or more. So that could actually, in the case of sepsis, make a very, very big difference. But the data in the sector is not taken that seriously yet. So a lot of doctors still count on their intuition, and rightfully so. It's very, very powerful. But it could be another tool, just like the stethoscope, just like any other tool that you use. Data could be another tool to help you in defeating sickness and defeating sickness. So I highly recommend we as a whole look into this, because it has a lot of cool applications. So thank you very much for listening. If you have any questions, post them in the chat. I see. Sorry, I need to leave. Thanks for the interesting talk. Okay, so interesting analysis of deep versus traditional machinery. Did you actually try deep learning algorithms on this data set? So yes, we actually did. We did do some deep learning algorithms on this data set, but unfortunately, like I said, I don't think we had quite enough data, because if you basically count the amount of actual time windows that we had to basically use as samples, that's not that much. So you might have an enormous amount of time windows in total, but you can only use as much as you have sepsis cases, and that's usually not that much. So we did do it. There are models out there, so definitely try them, but they weren't good enough in our case. All right. So if there's any more questions, thank you very much for the awesome feedback. I'll actually post the link of the paper in chat, just if you're interested, might as well. And then I'll also put my email address if you want to get into touch. That's fine as well. There you go. So anyway, thank you very, very much for listening. And if there's any more questions, I'll hang out a little bit more in the chat room. But yeah, enjoy the rest of the sessions and hopefully see you next time.